St. Joseph's College for Women Autonomous, Visakhapatnam, Department of Mathematics welcomes you for the online course on real analysis. Module 1 is real numbers, real sequences. My name is Dr. V. Gauri Shankar Rao, MSc MPhil PhD, Assistant Professor, Department of Mathematics, St. Joseph's College for Women. So let us see this Cauchy sequence. So what is the Cauchy sequence means? The Cauchy is invented by after some distance. In a sequence, after some distance, the two numbers distance is equal to 0. The two numbers distance is near to 0. The difference is the 0 or near to 0. It is called as a Cauchy sequence. So Cauchy means what is that? In a sequence, after some time, the two numbers distance, it is near to 0 or equal to 0. That sequence is called as a Cauchy sequence. Let us see this. A sequence Sn is said to be Cauchy sequence. For example, one sequence you can say it is a Cauchy sequence. In that time, if for each given epsilon greater than 0, there exists m belongs to capital N such that modulus sp minus sq less than epsilon for all p comma q greater than or equal to m. So what I said, the sequence, the two numbers, the difference is less than epsilon. Sp minus sq, the two numbers difference is less than epsilon or equal to 0. The less than epsilon means it is near to 0 value. For all p comma q greater than or equal to m. So in that time, this sequence is called as a Cauchy sequence. Example, 1 by n. So 1 by n, why can take as fraction means fractions always it is near to values. So for example 0 point like that. So that's why I can take that example is 1 by n. So theorem. If the sequence Sn is convergent, then prove that sequence Sn is a Cauchy sequence. Sn is the convergent sequence. What is a convergence means? Modulus Sn minus L less than epsilon. Once it is Sn is a convergent, you can say that sequence Cauchy sequence. Prove that Sn is a Cauchy sequence, or prove that every convergent sequence is a Cauchy sequence. Sequence is a convergent, so automatically it is the Cauchy sequence. You can say it is a Cauchy sequence. Let us see this simple proof. Let Sn be a convergent sequence which is convergent to L. Sn is a convergent sequence. Once it is a convergence, where it is at? L equal to L. So therefore limit n tends to infinite Sn equal to L. Condition for epsilon greater than 0, there exists m belongs to n such that modulus Sn minus L less than epsilon by 2 for all n greater than or equal to m. We have that one more doubt. So why? Because of actually condition convergence means what is that? Modulus Sn minus less than epsilon by 2. So I said epsilon means what is that? Near to 0 value. So epsilon by 2 also near to 0 value. The simple I can take epsilon, it is denoted by epsilon by 2. Whatever it is, the choice is yours. But here I can assume modulus Sn minus L less than epsilon by 2. So epsilon by 2 or epsilon both are the same, no problem. For all n greater than or equal to m, let p comma q belongs to n and p greater than or equal to m, q greater than or equal to m. Why? Because of the after some distance, the two numbers in between difference is the near to 0 or 0. So that's why sp minus sq. Here p greater than or equal to m, q greater than or equal to m. So this pq values must and should belongs to capital N. So then by the convergence property, can I write sp minus L modulus less than epsilon by 2. At the same time sq is the some value. Modulus sq minus L less than epsilon by 2. Here, what is the condition? Modulus sp minus sq. So modulus sp minus sq, can I write? I can add the minus L plus L. Minus L plus L is the 0. The both are the same. So after that I can divide as modulus 2. Sp minus L is the one module. The second plus sq minus L is the another module. So sp minus L means what is the value? Epsilon by 2. The same as it is sq minus L also epsilon by 2. Epsilon by 2 plus epsilon by 2, what is the value? Is the epsilon. So finally you can add the both. So modulus sp minus sq equal to epsilon or less than epsilon. So then Sn is the Cauchy sequence. So what is that? Cauchy sequence means sp minus sq less than epsilon. You are taken by individual convergence property. So then you can merge the two convergence. It is look like as a Cauchy sequence. Here you can remember that. So Sn is a convergence. The nearest values also it is look like as a convergence. That is a Cauchy sequence. Here what is the Cauchy sequence? In sequence, after some distance, before value minus after value minus before value, the difference is the nearest to 0, otherwise some 0. So in that time that sequence is called as a Cauchy sequence, whatever it is. For example, 101 term, 102 term is there, 102 term minus 101, it is near to 0 or epsilon. So that sequence is called as a Cauchy sequence. So let us see this theorem. If Sn is Cauchy sequence, then prove that Sn is bounded. Sn is Cauchy sequence, then prove that Sn is bounded. So Cauchy sequence, what you can prove that? Bounded. Bounded means you have that lower value at the same time upper value. So by the Cauchy sequence, modulus Sp minus Sq less than epsilon. Sp modulus is there, automatically lower value is there, at the same time upper value is there. They simply it is a bounded. So let us see the proof. Let Sn be a Cauchy sequence. Now we prove that sequence Sn is bounded. So since Sn is a Cauchy sequence, for epsilon greater than 0, there exists m belongs to n such that modulus Sp minus Sq less than epsilon for all p comma q greater than or equal to m. This is a condition of Cauchy sequence. So you can remember that modulus Sp minus Sq less than epsilon for all pq less than or greater than or equal to m. Actually n greater than or equal to m, but here you can take the two values. That one is Sp, one is another one is the Sq. So after some time, after some difference, Sp minus Sq. So consider modulus Sn. Can I write modulus Sn? Sn minus Sq plus Sq. So simply I can add minus Sq plus Sq. So after that you can individual. So can I take the modulus sharing on this? Modulus Sn minus Sq plus Sq. So modulus Sn minus Sq by the Cauchy means what is that? Epsilon. So this term is eliminated by epsilon plus Sq. So for all n comma q greater than or equal to m, here let capital M equal to maximum of modulus S1 S2 so on modulus Sn minus 1 comma epsilon plus modulus Sq. So in this sequence, in this set, I can take that maximum value. That maximum value treated as like capital M. So capital M means what is that infimum? I can take you are looking like capital M, na? So like mm equal maximum. So modulus Sn less than m for all n belongs to capital N. So modulus Sn means this is m valid from minus m to capital M, minus capital M to positive capital M. So automatically minus m is there, capital M is there. Automatically the sequence Sn is bounded. So therefore the Cauchy sequence, Sn is a Cauchy sequence, then sequence Sn is also bounded. Note, the converse of the above theorem is not true. Why? Because of the bounded sequence is not a Cauchy sequence. So bounded sequence is not, convergence is a bounded. Bounded is not a convergence, some particular reasons. So Cauchy sequence is not a Cauchy sequence is a bounded. Bounded is not a Cauchy sequence. Why? Because of bounded means the two limit points is existed, like lower and upper. So that is every bounded sequence need not be a Cauchy sequence. So example, minus 1 power of n. Why? Because of minus 1 is a one limit point, 1 is another one. The two limit points is existed. So that's why it is not a convergence. Let us see this one more theorem. If sequence Sn is a Cauchy sequence, then prove that sequence Sn is convergent. Sn is a Cauchy sequence. What you can prove that Sn is a convergent? Before one is Sn is a convergent, you can prove Sn is a Cauchy sequence. So here you can take that Sn is a Cauchy sequence, you can prove Sn is the convergent. Sn is a Cauchy sequence. Once Sn is the Cauchy sequence, already it is proved. Sn is the bounded. So once Sn is the bounded, so it is not a convergent, but when it is a convergence, only at least one limit point existed. One limit point is existed, in that time you can say it is the convergent. But the two limit points existed, it is not a convergence. Let us see that. Let L dash be another limit point of the sequence Sn. So actually bounded means the two limit points. One is the L, the second one is the L dash. Both are the same. You can prove L equal to L dash, the single limit point is existed. So that process I can move. Let L dash be another limit point of the sequence Sn. Now we prove that L equal to L dash. The both are the same, automatically single limit point is existed. So suppose L not equal to L dash, contradiction related. So already it is a proved related theorem. Let epsilon equal to, I can assume, modulus L minus L dash by 2. It is value is the greater than 0. Let limit Sn equal to L. So for epsilon greater than 0, there exists m belongs to capital N such that modulus Sn minus L less than epsilon for all n greater than or equal to m. This is the convergence property. So convergence property means what is that? Limit n tends to infinite Sn equal to L. So at the same time L is a one limit point, L dash is another. So both are the one is a small, the second one is a big. So both limit points is equal, it is automatically convergence. You can prove like that. So therefore L dash is a, since L dash is a limit point of Sn, implies Sn belongs to L dash minus epsilon, L dash plus epsilon for an infinite number of values of n. The two numbers existed, automatically you can minus epsilon or plus epsilon. So L dash minus epsilon less than Sn less than L dash plus epsilon. This is the lower value and this is the upper value. The lower and upper in between Sn existed, it is called as a bounded for an infinite number of values of n. So how we can write this one? It is nothing but modulus Sn minus L dash less than epsilon for an infinite number of values of n. So consider modulus L minus L dash, I can take minus n Sn plus Sn. So after that modulus I can shift Sn minus L, L minus Sn, it is a modulus. Can I write Sn minus L also? The both are the same. Sn minus L dash. Here Sn minus L convergence property, what is the value of this? Epsilon. And this value of the epsilon. Epsilon plus epsilon is the 2 epsilon. 2 epsilon value is equal to L minus L dash. So you are taken L not equal to L dash. But what you can prove? L minus L dash less than modulus L minus L dash. So this is not true. So this is not a true. So this is due to our supposition that L not equal to L dash. So therefore Sn has only one limit point. So therefore Sn is sequence Sn is convergent. So L is a one limit point, L dash is another limit point. What you can take? L not equal to L dash. But here you are proved L minus L dash equal to 0. Automatically L equal to L dash. So that's why your supposition is wrong. So only the single limit point is the existed. Once you can observe that the both are limit point is the different. Once you can apply the property so that both limit points is the equal. So that's why the single limit point is the existed. Let us see this Cauchy's convergence criterion. So what is the Cauchy's convergence? So Cauchy's convergence means a sequence is convergent if and only if it is a Cauchy sequence. A sequence is a convergent if and only if it is a Cauchy sequence. Once it is a Cauchy sequence, it is a sequence. It is a sequence, it is a Cauchy sequence. So let us see this theorem. Cauchy's general principle of convergence or Cauchy's theorem. Cauchy's general principle of convergence, it is means some like formulas. A sequence Sn is convergent if and only if to each epsilon greater than 0 there exists m belongs to z plus such that modulus Sn plus p minus Sn less than epsilon for all n greater than or equal to m and p greater than 0. So a sequence Sn is convergent. So once it is a convergent, what you can prove? Epsilon greater than 0 there exists m belongs to z plus such that Sn plus p minus Sn less than epsilon. Actually we are proved Sp minus Sq less than epsilon, but here taken by n plus p. The both are the same. So write the proofs of the before two theorems proofs and continuation. Already we are proved by convergent is the Cauchy sequence. Cauchy sequence is the convergence. The similar theorems we can prove here. So next one is contractive sequence. So a sequence Sn is said to be contractive if there exists C belongs to R, 0 less than C less than 1 such that modulus Sn plus 2 minus Sn plus 1 less than or equal to C less than or equal to Sn plus 1 minus Sn for all n belongs to n. So this C is in between n plus 2 term, n plus 1 term. N plus 1 term minus nth term. Actually you can see this nth term after n plus 1, highest value minus lowest value in between C. So this one is called as contractive sequence. So let us see this one more theorem. Prove that every contractive sequence is a Cauchy sequence. Every contractive sequence is a Cauchy sequence. Let Sn be a contractive sequence. Now we prove that Sn is a Cauchy sequence. Cauchy sequence is a contractive sequence is the Cauchy's. That is, for each epsilon greater than 0, there exists m belongs to z plus such that modulus sp minus sq less than epsilon for all p comma q greater than or equal to m. So this is a Cauchy sequence principle. So since contractive means, what is that? Be a contractive means there exists 0 less than c less than 1. C is exist on in between 0 1 such that in that time Sn plus 2 minus Sn plus 1 less than or equal to c in c modulus Sn plus 1 less than Sn. So for example, this is the highest term less than or equal to c into this term for all n belongs to capital N. So modulus Sn plus 2 minus Sn plus 1 less than or equal to c, this value is less than or equal to c into Sn minus 1. The since why? Because of what is the property of contractive sequence? Sn plus 1 minus Sn less than c into Sn minus 1. So both you can multiply this. C into c is the c square modulus Sn minus 1. So applying successively, we have modulus Sn plus 2 minus Sn plus 1 less than or equal to c power of n modulus s2 minus s1. So modulus sp minus sq equal to, here I can add minus sp minus 1 plus sp minus 1. So this one it can be written as like minus sp minus 2 plus so on sq plus 1 minus sq. So for pq belongs to capital N and p greater than q. So this one it can be written as, it is nothing but less than or equal to sp minus 1 plus, you can separate the modulus on each and every term, these two terms, and sp minus 1 minus sp minus 2, and the last term is the sq plus 1 minus sq. Modulus you can share the each and every term. After that, it can be written as less than or equal to c power minus 2 modulus s2 minus s1, the terms, the combination of constant like terms. So e power of minus 3 p minus 3 modulus s2 minus s1, so plus so on c power q plus 1 minus 2 s2 minus s1. You can separate these c terms, you can write 1. So these are like modulus s2 minus s1. The simple you can take as like common. So this terms is up to c power of q minus 1. So c power of q minus 1 it can be written as like this. So after term is modulus s2 minus s1. So here c power of q minus 1 into, so you can take the c power of q minus 1 it as like common. You got 1 plus c square so on plus c power p minus q minus 2 plus c power p minus q minus 1 modulus of s2 minus s1. So this series you can written as 1 into 1 minus c power of minus p minus q by 1 minus c. So modulus s2 minus s1. So since 0 less than c less than 1 implies c power of p minus q equal to 0. So this one it can be written as, so already taken by Cauchy sequence modulus sp minus sq. So what you have less than or equal to c power of q minus 1 by 1 minus c into modulus s2 minus s1. So it is like concretive sequence. So modulus sp minus sq less than or equal to c power of q minus 1 by 1 minus c modulus s2 minus s1. So therefore sequence Sn is a Cauchy sequence. So let us see this one problem. Show directly from definition that the sequence n plus minus 1 power of n by n is not Cauchy sequence. You can say it is not a Cauchy sequence. Let our assumption Sn equal to, what is that? N plus minus 1 power of n by n. Sn plus 1 means n is simply replaced by n plus 1. So after that modulus Sn plus 1 minus Sn. Actually modulus Sn plus 1 minus Sn less than epsilon. Let us see this. You can apply this. You got 1 plus minus 1 power of n plus 1 by n plus 1 plus minus 1 power of n plus 1 by n. So this series it can be written as less than or equal to 1 plus 1 by n plus 1, and this one is a 1 by n. So how we can write this one? Less than 1 plus 1 by n plus 1 by n. This total series it can be written as, so less than 1 plus 2 by n. So it is equal to 1 plus 2 by n. This value is less than epsilon. So once it is a less than epsilon, the sequence Sn is not a Cauchy sequence. Cauchy sequence means less than epsilon, but this value should be 1 plus 2 by n less than epsilon. So the directly by using this definition, the given one is not a Cauchy sequence. The symbol you can observe this, there is a minus 1 power of n is there. Once you can take the minus 1 power of n, automatically that negative value is there, at the same time positive value. It is an oscillation series. Once it is an oscillation series, how we can say it is a Cauchy sequence? So like that. Let us see this one more problem. Prove that the sequence Sn equal to 1 plus 1 by 2 plus 1 by 3 plus so on plus 1 by n is not convergent. So this sequence we can say it is not a convergent. Let us, Sn is the given sequence. So sequence Sn is convergent by Cauchy's general principle. Convergence for epsilon equal to 1 by 2 greater than 0. There exists m belongs to n such that Sn plus p minus Sn modulus less than 1 by 2. For all n greater than or equal to m, p greater than 0. So this entire value less than 1 by 2. For 1 by m plus 1 plus 1 by m plus 2 so on 1 by m plus p less than 1 by 2. So once it is a 1 by 2, can I write 1 by 2 greater than this total series? So 1 by 2 is a big one. Can I write like this also? So after that, so 1 by m plus p, each and everything you can remember that m plus p. So this total series is p by m plus p. Here 2m by m plus 2m, p is replaced by 2m, you got 2m by m plus 2m. So after that m plus 2m is a 3m, so both m values is a cancel, you got 2 by 3. So actually what they can set is a 1 by 2, but what you can prove 2 by 3. So 1 by 2 is a big one comparing to 2 by 3. So this is not a true. So therefore this is due to our supposition that Sn is convergent, but the finally what you have that not a convergent. So once 1 by 2 it comes, our assumption it is a convergent, but what you have that 2 by 3 is there, so it is a contradiction. So therefore Sn is not a convergent. Let us see this one more problem. Apply Cauchy's general principle of convergence to show that the sequence an where an equal to 1 plus 1 by 2 square plus 1 by 3 square plus so on plus 1 by n square converges. Cauchy's general principle you can apply. So you can say that the sequence an is convergence. By using convergence, Cauchy's convergence principle is convergence, where you can show this sequence also convergence. So an equal to the given sequence. So let epsilon greater than 0, n comma p belongs to n. Consider what is the condition of Cauchy's sequence? Modulus an plus p minus an. So already it is a given an plus p sequence, you can write n is replaced by something n plus 1, whatever it is. You can write like this sequence. So the next sequence you can write 1 by n plus 1 whole square like up to p by n plus 1 whole square. Here p equal to you can treat as like n plus 1. So n plus 1 by n plus 1 whole square, the both n plus 1 is a cancel, what you have 1 by n plus 1. So 1 by n plus 1 comparing to less than epsilon. So if n greater than 1 by epsilon minus 1, choose m belongs to capital N, there exists m greater than 1 by epsilon minus 1. So modulus an plus p minus an less than epsilon for all n greater than equal to m. So once you can remember that the Cauchy's general principle is a convergence, automatically the sequence also convergence. Why? Because of each and everything is relevant to convergence relevant. So once it is a less than epsilon, it is a convergence. For example, 1 by epsilon is there, 1 by some particular value, epsilon is not relevant to 1 by something values. In that time it is not a convergence, but in this case it is a convergence. So let us see this Cauchy's first theorem on limits. So Cauchy's first theorem on limits. So Cauchy's first theorem on limits means if limit Sn equal to S, if limit Sn equal to S, then limit n tends to infinite S1 plus S2 so on Sn by n equal to S. Limit Sn equal to S, at the same time by n also S. So this is Cauchy's first theorem on limits. So define the sequence Sn such that limit Sn equal to S. What the given one is you can define. So limit Tn equal to example. So for example you can consider some more sequence. That sequence is limit Tn equal to, Tn means can I write Sn minus S. Limit Sn minus S. Once you can apply this limit Sn minus S. Limit Sn means what is the value? S. Then S minus S equal to 0. The finally you got limit Tn value is the 0. So you are defined like this. So limit Tn equal to 0, limit n equal to 0, it means convergence now. So there exists m belongs to n such that modulus Tn minus 0 less than epsilon by 2 or epsilon whatever it is for all n greater than or equal to m. So limit Tn equal to 0, that implies Tn is bounded. So why you can say that the convergence automatically it is a bounded. You define Tn. So actually limit Sn equal to S, you are defined by limit Tn. Tn means Sn minus S. So that existed value is the 0. So once it is a convergence, you can prove it as it is like bounded. So bounded means the least value existed and highest values also existed. There exist k belongs to R such that modulus Tn less than k for all n. So consider, so this Tn, it can be written as T1 plus T2 plus so on Tn by n. So what you can consider by n? So you can prove like this one now. So already it is relevant 1. So by n, I can take like by n. So this is up to Tn terms, Tm plus 1 and Tn by n. You can separate the two up to Tm terms. The second one is the Tm plus 1 terms up to Tn. For example, this is the 200 series. You can take up to 100, then you can take 101 to 200 like that. So this consideration term you can split as a 2 terms. So then you can apply the modulus on the two separate terms. The first term is up to Tm by n. The second term m plus 1 to up to Tn by n. Like this is up to 100, this is up to 200 like. So this is modulus T1 means the particular value. That particular value you can treat it as like some k. So k plus up to k by n. So Tm plus 1 they can treat it as like some epsilon by 2. Already it is approved. Epsilon by 2 so on epsilon by 2. So k terms up to m. Up to m. So that's you can write mk by n. So this terms up to n minus m by n. N minus m by n into epsilon by 2. The simply, for example, the total 100 chocolates is there. So you can remove that 50. So it is look like as n minus r na. So like that. So after that less than mk by n. So this value is the epsilon by 2. So therefore n minus m by n equal to, can I write 1 minus m by n less than 1. So this value is less than 1. So n minus m by n into epsilon by 2 less than epsilon by 2. So by this case mk by n, so this value is m by epsilon by 2. Mk by n, this total value it can be treated as epsilon by 2. So it is nothing but n greater than 2mk by epsilon. It means m1 is the small value comparing to n. Let q equal to maximum m comma m1. Q is the maximum m comma m1. Here maximum m means what is that? This values. So T1 to so on Tn. So finite is the 0. So ln Sn minus 0 less than epsilon like that. So this is equal to 0. So this total value limit to T1. So T1 means what is that? Already you consider S1 minus S. T2 means S2 minus S. You can replace it by T1, T2 values. You got like this. So after that this total terms it is as minus S minus S minus S. They're up to n. Ns by n. So before sequence is the S1 to so on Sn by n. So nn is a cancel by s. It is the limit point is the 0. Once you can shift the s on right side, limit s1 plus s2 so on Sn by n equal to s. In this property you can remember that the 200 sequence is there. You can split that 100 and 101 to another one. So this 101 you can treat it as like k is a constant like. So these values they can teach as a epsilon by 2. So this is the same as it is. So this value is near to epsilon by 2. So after that limit point is a 0 already existed. What you can consider? So Tn equal to Sn minus S na, that property you can apply here. So automatically S1 is a separate and S is the separate. N is a cancel. You got that S is the existed. See this one more theorem. So if Sn greater than 0 for all n belongs to Z plus and Sn equal to L, then prove that limit S1 to S2 S3 so on Sn power of 1 by n equal to L. Sn is the greater than 0. So and Sn equal to L. You can prove power of 1 by n also finite value. So Sn greater than 0 for all n belongs to Z plus and limit Sn equal to L. If L equal to 0, case 1 you can take if L equal to 0. So we know that Am greater than or equal to Gm implies Am of S1 to S2 so on Sn greater than or equal to Gm of S1 to so on Sn. So this one is arithmetic progression. You can write like S1 plus S2 plus so on Sn by n greater than or equal to. So this one geometry progression you can written as S1 S2 so on Sn power of 1 by n. So already they said Sn is the greater than 0. So automatically this value is bigger than the 0. So 0 less than or equal to S1 S2 so on Sn power of 1 by n. So this value is comparing to power of 1 by n. This value is the big one. So automatically this power of 1 by n, it is 0 less than or equal 0 less than S1 S2 so on Sn power of 1 by n less than 0. By Cauchy's first theorem on limits, by the sandwich theorem, so limit S1 to S3 so on Sn power of 1 by n is the 0. So sandwich theorem means what is that? Sn is the 0 and Tn also 0, automatically the middle value Un also 0. By the sandwich theorem, 1 is the finite value, automatically the second sequence also finite. So then comparing to these two sequences, third sequence is also 0. So that is the sandwich theorem. Case 2. If L not equal to 0, before case is the L equal to 0 and this one is the L not equal to 0. It is like reverse order. Am greater than or equal to Gm, Am of 1 by S1, comma 1 by S2, so on, 1 by Sn greater than or equal to Gm of 1 by S1, comma 1 by S2, so on, 1 by Sn. So this is the arithmetic progression of this. This is the geometric progression of this. You can written as 1 by S1 to S2, so on, Sn power of 1 by n. It is like reverse. You can move on like less than. This is greater than or equal to. You can change on less than or equal to. This series it can be written as n by. You can do that like n by S1 plus S2, so on, plus n. So less than or equal to 1 by. This is reverse. S1, S2, so on, Sn power of 1 by n less than or equal to this total term 1 by n. So in between, for example, this is Sn, this is Un, and this is the Tn. So this value is the finite, automatically this value also finite. The both are the finite, automatically the third value should be same. This is a sandwich theorem. So this sequence you got that L. So this sequence, once you can apply the limit, you got that L. Automatically third sequence need not to be proved. Just simply you can say this one also L. So that is a by sandwich theorem. Limit S1 to S2, S3, so on, Sn power of 1 by n also L. So this is the sandwich theorem for. Let us see this. Cauchy's second theorem on limits. If Sn is a sequence such that Sn greater than 0 for all n belongs to Z plus and limit Sn plus 1 by Sn equal to L, limit nth root Sn equal to L. So Cauchy's sequence means what is that? Second theorem, limit nth root Sn equal to L. So by the condition Sn greater than or equal to 0 for all n belongs to Z plus and limit Sn plus 1 by Sn equal to L. So define the sequence Tn. T1 sequence, how we can define T1 equal to S1, T2 equal to S2 by S1, T3 equal to S3 by S2, so on, Tn equal to Sn by Sn minus 1. So numerator value is a big and denominator value is a comparing to numerator is a small. So consider T1, T2, T3, so on, Tn. So this values you can sub to up to Sn. So therefore limit Sn plus 1 by Sn equal to L. So implies limit Sn by Sn minus 1 equal to L. So big value by small value, big value by small value, it is a finite. So automatically limit Tn equal to L, limit T1, T2 power of Tn power of 1 by n equal to L. So limit Sn power of 1 by n equal to L. So it can be, it is nothing but limit nth root Sn equal to L. So by the condition big value by small value equal to finite, automatically that nth root value power of 1 by n value is also finite. So this is a Cauchy's second theorem on limits. Let us see this Cicero's theorem. So Cicero's theorem said if limit an equal to a, limit an equal to a, limit n tends to infinite, that value is the a. So limit n tends to infinite bn equal to b, the product, then limit a1 bn plus a2 bn minus 1 plus so on plus an b1 by n equal to ab. So the product divided by n also you can put say ab. So let us see this. What the given one is define alpha n equal to an minus a. I can define like that. I can apply the limit on both sides. Limit alpha n equal to limit an minus a. An value already they can define a. So limit an value is a minus a equal to what is that? 0. So limit alpha n equal to 0. Once limit alpha n equal to 0 means what is that? Convergence. The limit modulus alpha n equal to 0. By Cauchy's first theorem by n. Limit modulus alpha 1 plus limit alpha 2 plus modulus alpha n by n equal to 0. So by Cauchy's first theorem on limits. So next second, what is that? Limit bn equal to b. Limit bn equal to b means automatically it is a convergence, then bn also bounded. So bounded condition, there exists k belongs to R such that modulus bn less than k. So consider, so this is the bounded sequence. The first one is the convergence related, the second one is a Cauchy's first theorem, the third one you can take that bounded. So let us see this. Consider limit a1 b1, the right side term look like an bn by n. So limit you can apply. A1 means what you can consider? Alpha 1 plus a, bn as it is. A2 means alpha 2 plus a, bn minus 1 is as it is. An means alpha n plus a. So after that, a and bn is a, you can write like that. Alpha terms you can write the combination of. Alpha is the combination terms and remaining constant terms look like as a combination by n. All are the addition, you can write like that. So after that, limit you can share that first term and second term. So first term already they set it, this total value treated as like AB. So this value by n is there, 1 by infinite is what is that, 0. So then AB plus 0 equal to AB. So limit an equal to a, limit bn equal to b, then limit a1 bn plus a2 bn minus 1 plus so on, an b1 by n equal to ab. Let us see this one problem. Prove that limit 1 by n into 1 plus 1 by 3 plus so on plus 1 by 2n minus 1 equal to 0. So here I can take that nth term is called as Sn. So I can put n equal to 1, I got s1 equal to 1. I can put n equal to 2, I got s2 equal to 1 by 3. Now we can take that limit. So 1 by 2n minus 1 is there. So once you can replace n turns to infinite, you can take that n is the common. So that's why n into 2 minus 1 by n. Now we can replace, n is replaced by infinite. So 1 by infinite value is what is that, 0. By Cauchy's first theorem on limits, limit s1 plus s2 plus so on Sn by n equal to 0. So therefore this total term it is the 0. By the Cauchy's first theorem on limits, by using limit property you got that 0. Let us see this one more problem. Prove that limit 1 by n into 1 plus 1 by 2 plus so on plus 1 by n equal to 0. Here the same, Sn term is the 1 by n. You can put n equal to 1, you got s1 equal to 1, n equal to 2, s2 equal to 1 by 2. Now we can apply n tends to infinite, 1 by infinite is the 0. By the Cauchy's first principle, 1 by n is there, automatically n is replaced by infinite, that value is the 0. So once it is a 0, that value should be existed, it is a convergence. So let us see this problem. Prove that limit n tends to infinite, 2 by 1, 3 by 2 whole square, 4 by 3 whole cube plus so on, n plus 1 by n power of 1 by n equal to e. Here nth term treated as like Sn. Here you can put n equal to 1, you got 2 by 1, n equal to 2, 3 by 2 whole square. So nth term is the Sn. Now we can apply that n tends to infinity, this value is the e. So this total series it is equal to e. So like that, 2, 3 by 2 whole square and whatever it is, the final answer is the e. So each and every problem you can solve this method. Let us see this one more problem. Prove that limit nth root n equal to 1. So limit nth root n equal to 1. Again you can take Sn equal to n. So Sn plus 1 by Sn. Nth term is n plus 1. N plus 1 term is the n plus 1. Nth term is the n. N plus 1 by n. But directly no need to substitute that infinite. You can simplify 1 plus 1 by n. Here 1 plus 1 by n. Now we can take the limit on limit Sn plus 1 by Sn. So what is the value of this 1 by infinity is the 0. The final value is the 1. By the Cauchy's second theorem, limit nth root n value is the 1. So again the second problem. Prove that limit 1 by n into 1 plus 2 power of 1 by 2 plus 3 power of 1 by 3 plus so on, n power of 1 by n equal to 1. Here what is nth term is the Sn. Here you can put n equal to 1, you got that 1. N equal to 2, 2 power of 1 by 2. N equal to 3, 3 power of 1 by 3. So each and every value, once you can substitute that limit value, limit n power 1 by n equal to what is that? 1. So therefore, by Cauchy's first theorem on limits, so this total limit value is the 1. So this is the Cauchy's first theorem on limits. You can prove finite value. Thank you all watching this video. Thank you.